Welcome, amazing students. Mr. Viteri here, back at it again with the Unit 9 Day 2 presentation. Today, we're going to dive into the greenhouse effect, global climate change, global warming, all these terms kind of intermingled together. So, our climate is changing. The driving force behind climate change could be attributed to the greenhouse effect. So, what is the greenhouse effect? Remember the layers in the atmosphere as we spoke of before: troposphere, mesosphere, stratosphere, mesosphere, thermosphere. Sorry. Um, the greenhouse effect occurs in the troposphere, so the layer closest to the Earth. Now, I like to think of it as a blanket. Okay. In the summertime, if you sleep with a very big blanket, you're too hot. In the wintertime, if you sleep with a very thin blanket, you're too cold. So you need that blanket the right size. The greenhouse effect is that blanket. And we actually need it on our planet in order to insulate heat and to keep life as we know it here. The problem is when that blanket gets too thick. If the blanket gets too thick, we're going to get too hot and basically cause the changes that are occurring today. Increased temperatures, melting ice caps, increasing sea level rises, species becoming extinct because they can't adapt as fast, droughts in other areas, flooding in other areas, more intense hurricanes. We'll go into those details later on. So, how is it occurring? Um, and it's occurring because, and it's occurring at a faster rate since the Industrial Revolution, um, due to the increase in these five greenhouse gases. Okay, so we need to know these greenhouse gases. They're very, very important. Some of them you know already. Carbon dioxide is one of them. The chemical symbol for that is CO2. Water vapor is also a greenhouse gas, chemical symbol H2O. Now, the thing about water is that water, we don't want to get rid of water. Water is like a constant, okay? And it doesn't really attribute to too much global warming because it's fast residence time in the atmosphere, meaning that it does go into the vapor form, but then it comes right back down. So we don't necessarily attribute water as causing global climate change. Okay, it is the most abundant greenhouse gas, which is a funny thing, but we don't really necessarily try to say, hey, we need to stop water in our atmosphere. We need it in our atmosphere. So let's look at the other ones: nitrogen oxides, CFCs. Yeah, CFCs are coming back. So not only do they destroy ozone, they are a POP, a persistent organic pollutant, which is basically very stable. So it stays in our atmosphere relatively a long time. Those are also greenhouse gases. Okay. But it's different from ozone depletion. Let's not put those two things together. All right. And methane, aka natural gas, aka CH4, the chemical symbol. So I need you to remember those. Methane will come back up. CFCs will come back up. Carbon dioxide is always there. You should know that. Okay. Like I said before, water vapor is a constant. We don't want to get rid of it. It has a low residence time in the atmosphere, so we don't necessarily consider it as causing a big problem. So let's look at this image right here and see how it's a blanket. Well, here is the atmosphere, and this cloud here would be the greenhouse gases. The sun is going to penetrate through, and the sun could either be absorbed or it could reflect. A lot of the sun's energy is reflected back into the atmosphere. So if it goes back into the atmosphere and it hits this big blanket, that heat stays trapped into the earth. When I talk about heat radiation, I'm talking about infrared radiation, IR radiation, not ultraviolet. It's different. Ultraviolet usually dealing with ozone, infrared dealing with the heat energy from the sun. All right. I like to think of it as infrared. Red to me is hot. It symbolizes warmth. Infrared is that heat energy coming from the sun. So if we have rises in carbon dioxide, if we have rises in emissions of methane, if we have rises of CFCs or methane or nitrogen oxides, then we're going to get a thicker blanket. The earth is going to get warmer and warmer, and that's what the data is showing right now. Human-induced global climate change, okay, at a faster rate ever since we started using fossil fuels. Let's continue. All right. Now, here's some heavy stuff. And I want you to try to understand it. So this is what's going to separate the apesters from, let's say, a typical person that knows about environmental science. There's something called GWP, and that's going to be global warming potential. It's a number, it's a unit of measurement used to gauge how effective a gas is at trapping the sun's energy.
Mr. Wilson, please call the main office. Mr. Wilson, call the main office.
So, for instance, carbon dioxide, and let's just give it the unit of measurement of 1. It does have a GWP, a global warming potential of 1. And we compare all the other gases to carbon dioxide. Okay, so if we take water out of the equations, carbon dioxide is the next most abundant greenhouse gas. However, its GWP, its global warming potential, in comparison to methane, is relatively low. Its comparison to CFCs, it's very low. All right. So if I were to say who traps better sunlight, carbon dioxide or methane, you should say methane traps much more sunlight than carbon dioxide. If it was just, let's say, one molecule. The reality is that there's like a bazillion carbon dioxide molecules and only like 100 methane molecules. But these guys are more effective at trapping sunlight than these individually. But the overall sum, carbon dioxide traps more than methane. I hope that made sense. There's a great video here that we should probably take some time to watch that video because this computer lady does a great job doing that. Now, you don't necessarily need to know how to calculate GWP, but just understand that carbon dioxide has a global warming potential of 1. Then we have methane. Okay. Also, everything else is pretty much more than carbon dioxide. All right. Okay. And it's in order. Okay. So if we go chlorofluorocarbons have the highest, CFCs are the highest. So they're even worse than methane. All right. Followed by nitrous oxides, then methane. So methane is much more than carbon dioxide, but CFCs are much more effective at trapping sunlight. So just interesting information. Okay, and we'll watch this video because I think it's very important. Okay, I thought there was better visuals on there, but what the video was expressing was basically a GWP is a number. Typically, that number, also part of the equation, is associated over a given amount of time. So we could say carbon dioxide's global warming potential over 20 years, or we could say methane's global warming potential over 20 years. Typically, in the graphs that we're going to see in our next slides, you're going to see that it is expressed in oh, oh, you're going to see that it's expressed in over 100 years. Once again, don't get boggled down by the specifics. It's really not that important. Just understand it's a number that indicates how much sunlight can be trapped. All right. I'm really trying to get to the next slide. Okay. It is a great slide here. All right. So this is a different image. This is a different image. So let's just look at this image up here. In this image up here, CO2 has a global warming potential of 1. Right? Now, a CFC, let's go all the way over here. I'll tell you what HFCs are in a minute. But a CFC, look at its global warming potential, 4,750. Look at this one, even more, 10,900. Isn't that crazy? Okay. Now, we no longer make CFCs. Instead, we replace them with HFCs. I expressed that in my last lecture. However, HFCs don't destroy ozone. However, they do have a very high GWP. Look at this HFC R23, 14,800. They trap a lot of the sun's energy. So I think we need to do better. Okay. So if we look at the greenhouse gas, that's important to know. GHG stands for greenhouse gas. GWP is global warming potential. It's showing us that CO2 has a global warming potential of 1. CH4, aka methane, is going to have a global warming potential of 23. Nitrogen oxides, 296. But once we get to the HFCs, oh my God, 12,000, 1,300, 22.2. Now, you're wondering why this image is here. This image is actually made by an industry indicating that the R32 brand, the R32 formula for HFC, is better than, let's say, using the R410A. What are you talking about, Mr. Viteri? Talking some nonsense. Let me explain. The refrigerant for particular air conditionings for your car, central air unit, because of state code, you may not be allowed to use R23. The only one that you may be able to use is R32. So this is like industry trying to show, look, this one has far less GWP than the R410A. Now, I mean, I'm going over too much detail, but I have to tell you why this exists, and let me explain. A car that was made 10 years ago might have a refrigerant system that requires R410A. The newer cars are designed to have more efficient parts and perhaps work on R32. You have an old central air unit, it might use something like an R23. So, because of the ingenuity of young, bright scientists, we continue to make products that are more efficient. I hope I hope I explained that properly. All right. Okay. So we want low GWP. Methane keeps coming up in regards to GWP because methane escapes from landfills. Methane is going to escape from our ocean. It's going to escape from our frozen permafrost because methane is trapped in the ground over ice. Ice is on top. And if the permafrost in the tundra starts to melt, that methane could secrete out into the atmosphere, causing a positive feedback loop of global warming. I hope I didn't give you too much. You can rewind that if you need to. Okay. And methane also comes from landfills. Methane also comes from fracking. So that's why methane is a big issue nowadays. Finally, I believe we talked about cow farts and methane coming from cow farts or CAFOs. And so if we need to worry about the methane concentrations that we make because they could cause or induce global warming at an accelerated rate from CO2. Okay, beautiful. So here's another image. Out of all of the greenhouse gases, all right, we have the majority in the atmosphere, and this is from the IPCC, is carbon dioxide, then methane, then nitrous oxides, and then these are the HFCs, CFCs. All right. But look, those small amounts of HFCs and CFCs, they contribute to a large amount of the global warming potential than anything else. Try to get that point through your head. All right, let's continue. Okay, out of all of those, all right, once again, the majority is going to be CO2. Okay, well, actually, in here, if we were to take water into consideration, it'd be the majority of water. And then this small 28% would be all the other gases. In this one, we're taking water out and we're saying, look, CO2 is huge, methane is huge, nitrogen oxides, all that stuff. Okay. So how do we make greenhouse gases? Well, the majority of greenhouse gases, aka CO2, because that's the big one, is made in transportation, vehicles, all right, machinery, all right. Then we have electricity and industry. But the thing that you need to know is transportation releases the most greenhouse gases. So therefore, if we can limit transportation, how do we do that? We take scooters, we take bus, we increase tolls, we increase the prices of gas. We make green taxes. We pay subsidies for hybrid vehicles, or we start, offering rebates on Teslas or electric battery vehicles. These are things that we would possibly do. We give, some some you know monetary incentives for people to travel together in a vehicle, like the hover lane. Okay, and we could do that over tolls. This will increase the people carpooling as opposed to taking single vehicles. All right. This will be our last slide for today. I'm going to read it to you. Okay. And this is straight from the CED. Global climate change caused by an excess of greenhouse gases in the atmosphere can lead to a variety of environmental problems, including rising sea levels resulting from melting ice sheets and ocean water expansion, and disease vectors spreading from the tropics towards the poles. Very well said. These problems can lead to changes in population dynamics and population movements in response. You should know that we've been talking about disease vectors traveling from the poles to the north and the south. You should know that the ice sheets melt. Ocean water expansion is something different that you may not have heard about before. It's really not that difficult. Just understand hot water takes up more space than cold water. Okay? That's pretty much it. So the ocean, as it warms up, just expands. All right? And if you live on an island or close to sea level and that ocean expands, that could potentially destroy your home. And so that is an issue. All right. You were an excellent class today. I will talk to you later.